Hi folks, I'm going to try to bust out these sample problems. Again, like with the other videos, it's really good for you to have this and have gone through this before looking at the solutions. I'll post these online like I did last time. But also it's real important to go through them before you either look at those solutions or watch the video. You really want to give yourself a chance to make your mistakes. If you don't, it's really hard to focus on what it is that you need to focus on. And really, you want to use it as a way to identify, hey, where do you need more practice? So you make sure you've gone through that. If you haven't, turn this off, go work on it, fight with it, struggle with it. That's where the learning happens. Then come back and figure out and fill in anything you need to fill in. But I do want to go through these fairly quickly. I think there's 15 of them. And particularly I'll take some time on the rational functions. And then a little bit later I'm going to post another problem from chapter 4 that somebody asked. So there'll be a couple of new postings for you guys. So we're going to start very quickly with the complex operations. Hopefully, again, these are things that you've practiced. So hopefully the complex operations are going to go fairly quickly. Solutions to sample exam 2. Okay, so the first is dividing complex numbers. And really this is the, division's always the worst of the three. The big thing to divide is we can't divide this denominator into the numerator. One, because this numerator has two terms, so we'd have to divide that denominator into both terms. But this denominator, even though it is a single complex number, it has two terms all by itself. So really, to get the division to work the way we're used to it working, it would be nice if this wasn't a complex number, if this was a nice, real number. The nice thing is we can make any complex number into a real number by multiplying by its conjugate. So instead of a minus b, we have a plus b. So that forms a complex conjugate pair. And really it sets up a difference of squares. So this is, a minus b times a plus b. So when you multiply those together, you're going to get your a squared minus b squared, your nice difference of squares. So 4 squared minus 2i squared over, and this just needs to be FOILed out. So 12 plus 6i plus 16i, plus 8i squared. So just good old-fashioned FOIL that one out. Now the big key is to remember that your I squareds turn into -1. Since I is the square root of -1, its square is just going to give you -1. And if you respond with, but it's not possible to square something and get a negative, in the reals, you're right. That's what complex numbers are for. So this does turn into 12 plus, combine like terms there, 22i plus 8 times -1. It's going to turn into a -8. Over 16 minus the 2 squared is 4, and the I squared turns again into -1. So 12 minus 8, once this is done, 12 minus 8 is 4, plus 22i over 16 turns into a plus 4 is 20. So now that this is a real number, we can perform that nice division, because it's only one term now. So get a nice 4 over 20 plus 22/20ths I. We really do want this a plus bi form, because this is a complex number, so we should put it in the form of a complex number to have an actual solution. Do reduce these if you can. It does turn into a 1/5 plus 11/10 I. And again, that's in your a plus bi standard form of a complex. Excuse me. So the key for your division of complex numbers is this complex conjugate, is making sure you've got that set up so it sets up the difference of squares, gets rid of the I in your denominator, allowing your denominator to become a nice real number, so you can then divide term by term to get those A and B values for your new complex number. And that really is, division's really the worst of them. Number 2 is multiplication. So if you've already done this, you can do multiplication. So that's almost backwards, the harder one first, but that's okay. Don't let that throw you off. But this, again, is just FOIL. You almost treat the I as if it was a variable, as if it was just an X or something. Except that whenever you square it, replace it with -1. So 7 times 2 is what? 14 minus 2i plus 21i minus 3i squared. And again, I'm just foiling that. So we get, what, plus 19i minus 3. And again, that I squared turns into -1. -3 times -1, that turns into a +3. +3 and 14 is 17 plus 19i. Unless I did something weird in the multiplication, and I'm not seeing it if I did. That's it. Oops. Oh, you can see the bottom of that. I'm sorry. So again, just foiled it. Firsts should be outer and then inner. I like doing the inner first for some reason. So -2i plus 21i. And again, the key here, this is a -3i squared, but that I squared just becomes -1. Then you're just doing that multiplication and collecting like terms. The -2i and the 21i become 19i. Again, just like terms. That does become a +3. 14 plus 3 is 17. 17 plus 19i. A lot of people, I notice, tend to miss problems like number 3 because they make it far too difficult. People will see this problem and start foiling. This is a subtraction problem. You've got 8 minus 3i minus, if you distribute that 7, it's -7 minus 3i. It's just a subtraction problem. Don't make it worse than that. 8 minus 7 is 1. -3i minus 3i is -6i. Yeah, -3i minus 3i minus 6i. Now that's it. It's the same thing you'd get if you had 8 minus 3x minus 7 plus 3x. Nothing weird happens there, but a lot of people see that subtraction. They think they should be doing something more complicated, so you end up foiling instead. Make sure that doesn't happen to you. I don't think it helps that you go from the division to the multiplication to the subtraction. My guess is if those were written the other way, it would happen a lot less. That shouldn't matter, but sometimes things like that do. Okay. Number 4. Now, number 4, you're given a function in graphical form. So you're given this nice function. And one of the things you're asked to do is label some points. So real quick, I'm going to label some points here. That's 2, 0. This point up here looks like 1, 2, 3, 4. 1, 2, 3, 4. That looks like 4, 4. This point looks like 0, 4. This point looks like 1, 2, 3, -4, 0. Well, I wasn't feeling too creative. Oh well. That's okay. So this is our function f. What we're asked to do is draw the graph of the new function f of x minus 1 plus 3. And to do that, we have to know what that -1 and what that +3 are doing to our graph. So you may remember that anything that's happening on the inside of the function is happening to our x's and y's. It's happening left and right. But also it's happening backwards. And that could be a little strange. One of the things I often tell students, if students want something to be going in the -1 direction. Well, really something is. The axes, because the function doesn't exist yet, we haven't gotten to the f yet, the axes are the only thing we can move. So there is something moving in the -1 direction. It's the axes that move in the -1 direction. What does that make the graph look like it does? It makes the graph look like it went 1 unit in the positive. And you can imagine if I took the black, that's the x and y axis, and moved them -1, it's going to make this thing look like all those points moved that direction. So that's one of the reasons that all the stuff in here happens backwards, or seems to anyway. It's also why if there's a coefficient out there, it actually compresses us instead of stretches us, because it stretches the axis, which makes the graph look like it compresses. So it is important to remember everything in here happens backwards. After the function exists, adding this 3 after we have y values, well, that just takes those y values and adds 3 to them. So it does exactly what it seems like it should. If you add 3 to a y value, to all the y values, that's going to make all those y values go up 3 units. So after shifting over this way, they're going to go up 3, up 3, up 3, and up 3. So the whole picture is going to look exactly the same. It's just going to move that way 1 and up 3. So if we try to draw our new graph, it would be nice to have some points to track. So let's go ahead and track some. This 0.04 is going to go over 1, so its x value is going to increase by 1 unit. It's going to go from 0 to 1, and that's going to go up 3. So that y value is going to increase by 3. So it's going to be over at 1 and up at 7. And again, that's just adding 1 to the x's and adding 3 to the y's. So 1, 7. Same thing is going to happen to this point down at 2. It's going to go over 1 to 3. So 1, 2, 3. Over to 3 and up 3. 1, 2, 3. And be at the point 3, 3. Same thing to 4, 4. It was at 4. It's going to move over to 1 to 5 and add 3 to the y value, 5, 7. Lastly, again here, it's going to move this way 1 unit, turning it from -4 to -3, or lined up with that. And then instead of being at 0, it's going to go up 1, 2, 3, up 1, 2, 3, 4, 5, 6, 7, up 1, 2, 3, and land right there. So again, we should have the same exact shape, just shifted a little bit to the right and 3 units up. Should label this point as well, just since we're here, -3, 3. You played with a fair amount of these in section 3, 5. And you also did reflections and stretches and compressions. You should be prepared for stretches and compressions as well. If you need to review that section, please do. For those of you who are going on to Math 112, all of the trigonometric functions are graphed with this kind of logic. What kind of stretches, what kind of compressions, what kind of shifts up and down, right and left. So this kind of logic is really helpful for a lot of the graphing and the graphical analysis that we do in this class. In 112 and beyond, it becomes pivotal to be able to think of and manipulate functions in this way. So this is not just some cute little trick to move graphs around. This is a very important idea and way of thinking and looking at how changes in value affect your graphs. So don't let this problem or this kind of problem fall on the wayside. Okay, I think I have time on this video to do number 5 real quick. 5 is a problem to be careful about because you're asked to use a very specific tool. Whenever you're asked to use a very specific tool, be sure you use that tool. I had an instructor once that had an analogy. If you're swimming the 100-meter backstroke and you swim a record time, but you did freestyle instead of backstroke, that doesn't mean you win. So if you're asked to use a particular technique, you got to use that technique, or I can't give you credit for it. And I always feel bad about giving zeros for you doing something correct that's just not what I asked for. I feel bad about it, but I do it. So in this problem, you are in number 5, you're given this polynomial, you are asked to use the remainder theorem. To find p at -2. Now I know you could take the -2, plug it in for the x's, and find the value. I know you can do that. I'm not interested in the fact that you can do that. I want you to use the remainder theorem so you can show that you know what the remainder theorem is, and to make sure you get practice using the remainder theorem. It's a very nice, very powerful tool that a lot of people kind of leave 111 without having in their bag of tricks, and it's a very, very, very nice tool to have. If you don't know what the remainder theorem is, or didn't when you looked at the sample, hopefully you went and looked it up. I know you had a couple problems with it, but if you need to go back and look it up, look it up. If you still don't know what it is, stop the video and go look it up. I'll give you a minute to do that. Hopefully you've done that. You don't want to wait for me to tell you. If you wait for me to tell you, you're not going to remember it as well. Anyway, the remainder theorem is a tool from our synthetic division, actually. If we want to know what this function is evaluated at -2, we can actually perform the synthetic division with the root -2. Now, normally, doing synthetic division with the root of -2, we're looking for that remainder to be 0 to show that it's a 0 of the polynomial. But that remainder, if it's non-zero, actually does tell us something very, very useful and very, very important. So use the value as given. Notice this isn't +2 that I'm using. I want the value at -2, so we're using -2 in our synthetic division. And set up our coefficients. Our coefficients are 2, 3, notice there's no x squared, so 0, 3, -2. I mentioned this on the last video I set out. It's really important to make sure you get those zeros in there. If not, the synthetic division won't work at all. So this is a 4th degree, so it should go 4, 3, 2, 1 constant. So make sure that happens. Okay, and then really quick, perform the synthetic division. Bring down the 2. 2 times -2 is -4. 3 minus 4 is -1. So 2, 2, -4, -1, and 2. Hey, we get 0. Well, that's handy. That means it's x plus 2 is a factor. Great for x plus 2. But it also tells us something else. It tells us that p evaluated at -2 is equal to 0. This remainder is the function evaluated at that value. If we'd have used something else, see if I can do this real quick, I have a minute left. If we wanted to find p at 1, we could do synthetic division with that 1. 2, 3, 0, 3, -2. 2, and do the synthetic division real fast. I'm going to do it real fast, I only got a couple seconds here. So 2, 5, 5, 5, 5, 8, 8, 6. Assuming I didn't do something wrong doing that too fast, that means p evaluated at 1 is 6. If you put a 1 in here, you should get 6. Heck, we can even do that real fast. 2 times 1 is 2, 3, 3, -2, so 2 minus 2 is 0, 3 plus 3 is 6. P at 1 is 6. This works for even very, very large polynomials. It's a great tool to have in your bag of tricks. We'll use it a lot in calculus and use it a lot other places. Okay, for question 6,